Hello everyone, I'm Jianren Wang from Carnegie Mellon University. Today, I'm going to talk about uncertainty-aware self-supervised 3D data association. This is joint work with Siddharth Encha, Eating Chen, and David Held. Traditional autonomous driving systems are composed of a set of modules, executed one after another. The vehicle first senses its environment as a LiDAR point cloud. A detection module is then used to estimate the locations of objects in the environment surrounding the vehicle. Further, in order to safely navigate in its surroundings, a data association module is used to associate detections with existing tracks to understand their dynamics. The results are then used for trajectory forecasting and motion planning. In this work, we focus on the problem of 3D data association. Given a set of existing tracks from frame 1 to frame t-1 and detections in frame t, the goal is to associate object detections in frame t with tracks that have the same IDs. Traditionally, data association is obtained using motion prediction, such as using a Kalman filter. Given a track, previous works first predict the location of the object in the next time step. Distances between the object detections and the prediction are then calculated using the probability and the predicted distribution. Given these distances, optimization algorithms, such as the Hungarian algorithm, are used for data association. However, this traditional approach does not use any object appearance information. Recent works propose to associate tracks with object detections based on appearance similarity. Convolutional neural networks are used to extract appearance embeddings of tracks and detections. The cosine similarity between these embeddings are used for data association. However, how to learn these appearance embeddings remains a big problem. State-of-the-art approaches require vast amount of labeled data associations across frames. Obtaining large-scale, human-annotated labeled data can be expensive and time-intensive. On the contrary, vast amounts of unlabeled data is cheaply available. For example, LiDAR sensors fitted on vehicles continuously collect and store data streams without requiring any human processing. A natural question is, can we learn 3D embedding from unlabeled data? And the answer is yes. In this work, we propose to leverage unlabeled data via uncertainty-aware self-supervised learning of 3D data association without the need of any labeled data. Here is an overview of our method. Given a large amount of unlabeled data, we first run a learned object detector on a large unlabeled dataset. We then perform self-supervised data association. To suppress the contribution of incorrect associations during self-supervised training, we propose uncertainty-aware weighting. Finally, we learn a point cloud embedding using the triplet loss, such that embeddings are similar for detections of the same object in different views, but are dissimilar for detections of different objects. We also propose to use hard negative mining to obtain a more robust embedding. We will go through each module in detail. First, we adopted a simple method using previous work to generate a proposed data association. As in previous work, we use a Kalman filter to track objects. We use the predicted distribution of object locations to match tracks with detections. The resulting associations are treated as pseudo-ground truths by our method. Given the estimated detections and associations, we wish to learn a 3D embedding from an arbitrary point cloud inside a bounding box. We first cropped point clouds that are centered and aligned using the bounding box locations and poses. Then, the point net is used to extract an embedding from a point cloud. We define two properties that the embedding must satisfy. Embeddings of bounding boxes of the same object across frames must be similar. Embeddings of bounding boxes of different objects across frames must be dissimilar. The similarity can be measured using the cosine distance of the embedding, where E1 and E2 are 3D embeddings of two different point clouds. Such embeddings will be used to associate detected 3D bounding boxes at test time for 3D tracking. In order to learn such an embedding, we use the triplet loss, which is defined as follows. Let EA be the embedding of an anchor detection in frame T, and EP be the embedding of the same object in another frame T plus K. Let En be the embedding of a different object in frame T, and M is a margin hyperparameter. The triplet loss is 0 when the cosine similarity between the positive pair is at least M more than the cosine similarity between the negative pair. The triplet loss encourages embeddings of positive pairs to be more similar to each other than embeddings of negative pairs. However, if the estimated detections and associations are incorrect, the learned embedding might be inferior. We then propose to estimate uncertainties during matching, which are further used to downweight potentially incorrect associations. Given a set of previous tracks in frame T-1 and detections in frame T, we need to first associate each track with the detection. The Mahalanobis distance is computed for every possible association pair. The detection that corresponds to the smallest Mahalanobis distance is greatly associated with the respective track. To calculate the uncertainty, we first find the most likely alternative detection with respect to the associated track. Similarly, we find the most likely alternative track with respect to the associated detection. The minimum ratio of these two distances to the associated distance is used to calculate the association uncertainty. Intuitively, the uncertainty compares the distance of associated pairs with the lowest unassociated distance if we were to choose a different track or detection. Then, we multiply the uncertainties between successive frames to get the cumulated association uncertainty across frames T and T plus K, which is further used to downweight the loss. We use higher negative mining to select negative examples in our triplet loss. Specifically, given an anchor embedding EA in frame T, we compute the cosine similarity between EA and all other embeddings in frame T. We choose the detections that has the highest cosine similarity with EA as the hardest negative example. Since this detection is in the same frame as the anchor detection, it is guaranteed to be a different object. At test time, self-supervised embeddings are extracted from each candidate detections in the frame. We use cosine similarity of embeddings extracted from each pair of objects to represent their appearance similarity. To perform multi-object tracking, we use a linear combination of motion information, detection confidence, and appearance similarity as the association score. The coefficients of the linear function are estimated via logistic regression, which classifies whether detection belongs to a track. We evaluate our method under two experiment setups, single object tracking and multi-object tracking. For single object tracking, we only use appearance similarity in order to isolate the benefit of our self-supervised embedding. We calculate the classification accuracy on Kitty using the embeddings trained with new scenes. We also evaluate the performance of our proposed multi-object tracker using AMOTA, a new scenes dataset. For single object tracking, we compare our method with two random baselines for sanity check. We randomly pick one of the candidate ground truth detection at each time step. An accuracy at about 25% suggested that there are 4 candidates on average per frame. For randomly initialized network embedding, we randomly initialize the weights of the point net architecture. We also compare our method with two supervised baselines, point net pre-trained with shape net classification and shape collision 3D tracking. As shown in the chart, our method, trained on unlabeled data, outperforms all of these baselines. The method of shape collision 3D tracking has performance near to that of our performance. However, their approach was trained on fully supervised data with ground truth detections and ground truth data associations. On the other hand, our method was trained on unlabeled data with estimated detections and estimated data associations, using uncertainty weighting and hard negative mining. To provide an upper bound of our performance, we also compare against using fully supervision, which is trained with ground truth detections and ground truth associations. This is the ideal case for self-supervised learning and achieves the oracle performance of our method. As shown in the chart, the performance of our proposed method is very close to the oracle. However, because our method can be used to train embedding on an unlabeled dataset, we could potentially obtain even better performance given a large unlabeled dataset on which to train our method. We perform an ablation to show the contribution of different components of our association score, the motion score, the detection score, and the appearance score. The results show that each component is important for accurate association. We perform another ablation analysis to quantify the performance of each component of our system. We remove one component of our training procedure at a time. We denote that either removing higher negative embedding or not incorporating uncertainty consistently reduce performance. This shows that both these components are useful for our method. We also verify the effectiveness of our proposed method for estimating association uncertainty. We can see that incorrect associations are with lower association score if the appearance embedding is trained with uncertainty weighting, and correct associations are with higher association score if the appearance embedding is trained with uncertainty weighting. We also compare our self-supervised embedding with baseline ShapeNet embedding qualitatively. The first column shows the exemplar anchor box. This denotes the car that is to be tracked. The middle column shows the bounding box selected by our method at each time step. The red column shows bounding boxes that the ShapeNet embeddings deem to be more similar to the tracked object. These examples show that the embedding learned using triplets via self-supervision is able to correctly match bound clause of the same object, even if the distractor object's bound clause is only subtly different. In conclusion, we propose a self-supervised representation learning method for 3D tracking and data association. We incorporate tracking uncertainty for robust self-supervised learning to handle tracking errors. Our method avoids the need for extensive manual annotation. Our self-supervised learning approach can make use of large unlabeled dataset. Please check our paper and project page for more details. Thank you.